All right, so whenever you're talking about ionic formula, we've always been reducing our subscripts to the lowest possible ratio because we're trying to indicate the best or the simplest ratio between two atoms to give us a formula. We don't always do that for molecular. Molecular is actually not the most reduced ratio, and it's because a molecular compound, which is a covalent compound, can have an even, a greater ratio than the simplest form because that's just how the covalent compound is arranged. So whenever you're looking at empirical formulas, many times you'll be given mass percent, and that mass percent of elements like carbon and hydrogen and oxygen. We don't deal with percents very well in stoichiometry. We actually generally just assume that I have a 100-gram sample of that whole entire compound. And when you assume a 100-gram sample, it makes your percents immediately turn to mass. So I have a 100-gram sample of something that's 25% carbon and so forth. I would immediately assume that's 25 grams of carbon. And once I know grams of carbon, I can get to moles quite easy. So when you take your mass that you assumed, you get to moles of each of the compound. Then you're going to have moles, moles, moles for this example here with CHO. Moles, moles, moles means I now can say, okay, I've got these to the point where I can make a ratio, because everything within a compound is a mole ratio. Like we've been doing intermole ratios, that's what this is. So to get them to the simplest ratio you can achieve, you divide each of the moles by the smallest of all the values. Basically dividing by you're finding the least common multiple, math term, okay? So that's what you're going to be doing. And once you get the values, so when you divide by each of the moles by the least value for the moles, that is going to be your coefficient. Not coefficient. That's going to be your subscript. I'm thinking reactions. That's going to be your subscript for that particular element in the formula. So the fourth step here, this is only if in step 3, when you get these values for the subscripts, if all of those are whole integers, you stop there. You're good. You get like a 1, a 2, and a 2. Those are your subscripts for your formula. But if you get like a 2.5, we can't have half of an atom in a formula. We just can't do that. We're not atom splitting yet. So we actually have to consider how to get that subscript up to a full number. So we're going to multiply it by an integer. So, and when you multiply 1, you multiply them all. Because if you started multiplying one subscript and you don't do the rest of them, you've skewed the ratio. It's no longer correct. So you'll do all subscripts whenever you're doing a multiplication. So if something ends in 0.5, you multiply them all by 2, you get them to full integers, you're good, that is your empirical. If something ends in like a 0.33-ish ending, then you'll multiply all those subscripts by 3, you'll get them up to a full integer. It will work out, I promise. We don't see this one too frequently, but if it ended in 0.25, 0.75, you multiply by 4, and they'd all end up to be a full integer. So most commonly, though, we probably see this one right here. So I'll have an example of that here shortly. And let's actually do a problem. I think it's the next one. Yeah. Are you guys ready? We're gonna actually do this now, okay? So let's start with, I'm almost 100% sure I have this on the paper. I could be wrong, but we're gonna go with it. So a sample of unknown compound has a mass of blah, blah, blah. It was analyzed and found to contain that much carbon, that much oxygen. Notice I actually went straight to grams here. What did I tell you? I could start you off with percent, and then you would assume a 100-gram sample. I actually got this down to the grams already, so we're good to go. So you guys are doing my human calculators, okay? So we have our sample. The mass is 2.571 grams total. And that total sample is containing carbon and oxygen. So I'm just going to put CXOY because I don't know what those subscripts are. That's just a disclaimer to myself. I know that's how the formula is going to look. It was found to contain 1.102 grams of carbon and 1.469 grams of oxygen. Yeah. All right, so step 1, take your grams and do what? Convert to moles. Okay. So carbon weighs what? 12.01 grams, and I think it's like 011 on your periodic table, but I'm going with my brain too. So we're looking at the molar mass from the periodic table and convert. I got you guys on the first one. 0.091757. Yes, I'm extending it because I'm not at my final answer. I don't have rounding error just yet. All right, so next one. We're going to keep that mole there because we need to do a mole comparison after we get to oxygen moles. So 1 mole of oxygen, just straight oxygen, not diatomic oxygen, this is elemental, is 16.00. And that is, anybody? 1825? 125. Is this right? Something, okay. Cool. All right, so what do we notice about these? They are like almost exactly the same. So I know that when I divide them by the smallest one, which is who in this case? The carbon, they're both going to be what? Really, really close to 1. So I'm going to divide this by itself, which is going to be 1. And remember, these are our subscripts. And when I divide this by the carbon mole, what do you guys get? Probably like 1 point. Yeah, like that's totally rounded to 1. There's no way that's not rounded to 1. So this was an easy one. We have our compound formula already. We have 1 carbon and 1 oxygen, CO, and that is our empirical formula because it's at its simplest ratio. Name is what? Carbon monoxide. Okay. And this number up here was not used because this was just simply information to say that's the sum of the mass of the 2 elements in that compound. Sometimes what I'll say is that's the total sample, and the sample contains carbon and oxygen, and I'll just tell you carbon. So then you would need that total to figure out the mass of the other element if I did not give that to you. That is empirical formula. All right, we're going to do molecular formula. I'm going to skip that for some for now. All right, so molecular formula, you do the same exact process. It's just at the end, you have to modify the formula a tad. So I'll let you read first and write what you need to. I'm videoing too. I'm going to look at this afternoon. So for a molecular formula, you have to up the ante. You have to take the ratio you got from your empirical formula, and you're going to multiply it by an integer to get to the molecular formula. All that integer will do is you'll multiply to all of the subscripts in the empirical formula. That's what you're going to do with the integer. But how do you get that integer? Basically, you look at the mass relationships between the molecular formula mass and the empirical formula mass, and there will be a multiple that gets used between the two. So you'll get the molar mass of the empirical formula and the molecular formula, and you'll take the molecular formula mass, you'll divide it by the empirical formula mass, and you'll get this integer, which we call n. It'll be, 2, 3, 4, 5. It will be close to a full integer. And you'll take your empirical formula and you'll multiply those subscripts by n, which is what I just wrote right here. And that will be your molecular formula. So, for example, CH2O is a general formula for a carbohydrate. And if I wanted to make it glucose, what would be my multiplier, just because you know what glucose formula is? 6. So that 6 came from taking the molecular mass of glucose, which is 180 grams per mole, I'm pretty sure, and dividing it by 30, which was the empirical formula of mass CH2O. So when you multiply that by 6, you get C6H12O6. So this would be the molecular formula. So you do exactly the same thing you do, it's just have you get some extra information, which I'll incorporate on, I think, the next problem. So this is just a sample. You've got your molecular mass of your molecular formula to be 250 grams per mole. But when you found the empirical formula, you added up the mass and you got it to be 125. So it's easy to see the multiple there, but you would take 250 grams per mole and divide it by 125 grams per mole, and you get the multiplier of 2, and that 2 is your subscript multiplier for incorporating it into the empirical formula to get the molecular formula. Is this coming back to some folks? Shake your heads or give me like this like scared eyebrow look. Yeah. Distribute. Yeah, good point. So I'm showing you how to do it, but you are going to distribute that to each of the subscripts, and this will be your final answer. Okay. All right. So let's take this one, and we're going to go from empirical to molecular. Okay. So you have an oxide of phosphorus. So it's got phosphorus and oxygen, but it's 43.7% phosphorus, and then it tells you for later use the molecular weight is 248 grams per mole. So the first, obviously, since the questions determine the molecular formula, but we cannot determine the molecular formula until we've determined the empirical. So step 1, empirical. You take your percent and you assume what? A 100 gram sample. Okay, so we know this is 43.7 grams phosphorus. What's the other percent? 50 what? 56.3% oxygen, because it's an oxide of phosphorus. So I want you guys to start first without me. Look at your steps. I want to calculate in the board too, but work from your paper. Yeah, you definitely need empirical. Is phosphorus 39 or 30.97? Give me a thumbs up. You made it moles. Right, check your answers of moles on up here. And we can see there's a relationship here. We can't really do that in our head very well. So what do we need to do? Divide by what? Who's that? The phosphorus. So we're going to divide both of these by 1.411. Well, that's 1. That's easy peasy. It's the same number. This is what? 2.49, which is basically 2.5, right? Can't have that as a subscript. So what do I have to do? But multiply both by 2 to get them to round to a full number. So that's going to be 2 as my subscript, and this is going to be 5 as my subscript. So I told you that's one of the more common ones. So these are the subscripts. What's the empirical formula? P2O5, name that. Diphosphorus pentoxide, or pentoxide if you want to say it like that. So that's our empirical formula. While I have the empirical formula up there, let's go and calculate the mass of that empirical formula because you know we're going to need it. Anybody? 0.94? Okay. So the empirical formula mass of P2O5, 141.94. Why was that important? Right, so we need to compare that to the molecular formula mass. I'm pretty sure you guys can see the multiple here. What's it look like the multiple is? 2. So that, you're going to put 141 into 284 twice. But just to show our work for that, we're going to say, what was it, 284? 284 grams per mole was the molecular formula mass, or the molecular mass as it's sometimes called in a question setting, divided by the empirical formula mass, 141.94 grams per mole, multiplier of 2. So this is N, which we're going to use as a distributive factor into our empirical formula. So P2O5 now gets a 2 on the outside. What's the molecular formula now? P4O10, because you're just distributing the 2 into both subscripts. Name this. Tetraphosphorus decoxide, or decaoxide. Decoxide sounds better. All right. Can I get a thumbs up for molecular? Coming back to you some. Okay. I think I have enough time to do all of combustion. I have big goals that we're going to try. All right, so this is for sure. So under as the third page back, combustion analysis. This is the newest topic. This is the new topic. The first new topic we've seen. Everything we've done so far has been old news. Maybe just reminding you of some of those like big internal mole ratios we get into that, but this is new. So combustion analysis is just an extension of molecular formula and empirical formula. The idea, though, is that this is in a reaction setting. So with that reaction setting, we have to consider how the carbon in the hydrocarbon reacted. Well, that's carbon's in the carbon dioxide now. And where did this hydrogen go in the hydrocarbon? It's in the water. Same thing happens with this hydrocarbon. This hydrocarbon has oxygen in it, which makes it a little bit more of a complex formula and a more complex problem, let's be honest. But the carbon, when it reacted, law of conservation of matter, matter's neither created nor destroyed, it's just rearranged. So this carbon became carbon dioxide, this hydrogen became water. This oxygen is in both of them. And so that's where, because oxygen comes in 2 places, it becomes a little bit more complex. So remember, combustion means to react with oxygen. So usually I'll have you write out the combustion reaction first just to get the hang of it and make sure you're remembering that. And then we're going to actually use data to determine, we're going to backtrack from products with their data, usually in grams. We're going to backtrack to find the molecular formula of the compounds that we combusted, the hydrocarbons. So an example will mean the world to you, so that's what my goal is to get to. So remember, when I say hydrocarbon, it can be either a hydrocarbon, which is CNH, or it can be a hydrocarbon containing oxygen, which means something like this, like a carbohydrate or glucose. So when we do combustion analysis, what we're doing is we're collecting the products, the carbon dioxide and water, we collect that and we analyze their composition to backtrack to the original formula. And I believe I have all that right here for you, so I'm going ahead because I printed this for you. So this is the contraption. This is what it looks like. We call these things U-tubes because they are tubes that are in a U shape. And remembering, all the carbon from the hydrocarbon goes into the carbon dioxide, and all the hydrogen from the hydrocarbon goes into the water. That's kind of the main point here that makes it a little bit more extensive. All right, so this is your set of guidelines. I'm giving this to you so you can follow it just like we follow empirical formula. Like that part down there. And you'll notice how similar it is to empirical molecular formula. And I put some of those in color-coded red because the black stuff up here, grams to moles of carbon dioxide to moles of carbon, that's our normal empirical formula, molecular formula thought. It's just I'm isolating carbon as a singular element from carbon dioxide, which we didn't do in the past. Same thing for water. Get your water to water moles, pull the hydrogen out of that using an internal mole ratio to get to just moles of hydrogen. Once we get there, we'll do our simple mole to mole comparison, divide by your lowest moles, get your formula. The red stuff here goes with if you have to consider a hydrocarbon with oxygen. So I'm going to work through a question like that too, but because we have a hydrocarbon which contains CH and O, and I usually know the mass of this, I know the total mass of that, I actually have to just subtract the mass of carbon, subtract the mass of hydrogen, I get the mass of oxygen by itself. And once you get something by itself, you can work with it to get to moles. So take a picture of that if you need to, finish writing down if you need to, and I'm going to do 2 problems in 7 minutes. No, I probably don't, but we'll work on it. I'll try anyway. I love when I try to get the labs back in and then I fail. It was worth a try. Yes. The first 2 examples are the 2 examples that are in the packet. All right, I will go back to that slide, I promise. All right, so a compound contains only hydrogen and carbon. Woo, this is an easy one. We have a sample, it's 1.45 grams, and it's burned, aka combusted. It's producing this much water and this much carbon dioxide. We're going to determine the empirical formula. This is example 1 in your packet. Okay, write down your little equation just to show yourself what's happening. Oops. So we're making carbon dioxide and water. Sorry guys, the perfectionist in me can't have red and purple on board. It's just not going to work. Okay. Alright, so I know everything. I know everything about this combustion formula, or combustion equation. I know this is 1.45 grams. I don't know what this is, but I can figure it out if I wanted to. I got 2.25 grams of water, and I have 4.4 grams of carbon dioxide. This is the easy one, but I would like for you to write this out first because this is how we'll start the ones with oxygens in them as well. So first step, take your grams of what? Carbon dioxide. I'll tell you carbon dioxide's molecular mass. 1 mole of carbon dioxide is 44.01 grams. Okay, we made it to moles. What do I do next? We made it to moles of carbon dioxide. Get moles of carbon from carbon dioxide. Well, what's the internal mole ratio inside of carbon dioxide? Right, 1 mole of carbon dioxide contains 1 mole of carbon because there's a subscript of 1 next to the C. Next up, write down 1 mole of carbon dioxide on the bottom, and there's 1 mole of carbon within that, and that's our internal mole ratio if you're trying to figure out how we get that. Stop here, calculate. That should be, I got calculations for you guys too, so it'll help me. 0.099977 moles of carbon. It's very similar to empirical formula. We just had to do this little conversion here. All right, water, 2.25 grams of water. Okay, molar mass of water. I heard 18.02-ish when you add it up. That's just you taking your molar mass there. Okay, so we made it to moles of water. I need to get to just simply hydrogen. So what's it looking like there with the internal mole ratio? 2/1. But 2 what? 2 moles of H, simply H, not H2 diatomic. It's just H as an element itself, because the internal mole ratio within the water, in 1 mole of water. So as you're saying, you have twice as much hydrogen. That matters. That is when you calculate 24986. Okay, and that's our hydrogen. So guys, we're just to the normal stuff. I got moles of one element, moles of the other element. How do I get the empirical formula? Divide by what? Who's smaller? The carbon, 0.099977, that's going to be 1. We're going to divide this one by 0.099977, that is, 2.5. What I got to do? Both of them, right? That's going to be 2 for the carbon, and this is going to be 5 for the hydrogen. What's the empirical formula? C2H5. And that's a hydrocarbon. We'll learn the organic chemistry nomenclature later. So what's different about combustion analysis so far? the internal mole ratio. I still start you off with grams, but I give you the big picture. The big picture sometimes scares people, but we're going to do another one. I think I have time for this. Do it. Let's go. 2. All right, same thing. Write down your equation, but now we have oxygen inside of our hydrocarbon. So an oxygen containing hydrocarbon. So we're going to write this like CX, Y, and then OZ plus oxygen yields carbon dioxide and water. Write your data. It says 9.57 grams of carbon dioxide, 5.87 grams of water, and this was a 5-gram sample. Occasionally I'll ask like how much oxygen was combusted with it, but you would just subtract the masses and get how much that was, but we're not going to do that right now. Let's start this off the exact same way. Take your 9.57 grams of carbon dioxide and convert to what? Moles, which is what? 44 grams per mole, 44.01 grams per mole. And then continue, what do you convert your carbon dioxide to? 1 mole of carbon internally for every 1 mole of carbon dioxide. Stop here, we're going to calculate first, and I've got you on the calculator. I've calculated all this for you just to help with our speeding up our process. So that is 0.2175 moles of carbon. Put a circle or square around that so you don't lose that in your work. I'm going to do the second one for water just the same way we did. So that is 5.87 grams of water. 1 mole of water is 18.02 grams of water, which is 2 moles of hydrogen inside of 1 mole of water. That is 0.6515 moles of hydrogen. Same exact steps we were doing earlier, right? The little caveat for when it contains oxygen is you had to also convert these to what? To grams. Because what we're going to do is we're going to compare these grams to what was in here, and we're going to see how much oxygen was in that hydrocarbon. So back to grams, right? So 1 mole of carbon, 12.01 grams of carbon is, forgive me, I'm going to write it down here, 2.6115 grams of carbon. I will finish this on the video. Watch the last 5 minutes of this video, okay? I'll update the website with homework later. I will have to modify some things. Okay. These, I'm just going to finish talking to myself and solving this in this video. Okay? That's what I'm going to do. Have a great long weekend, but we'll update the homework, okay? Let me check in my book. It's not in the box, is it? I don't think I passed it back to somebody else. Hold on. Hold on. 0.10.
Have a good weekend.
Bye. Thanks, you too. Just hold on, I'm writing in the board. I can't talk to you and write this. It's right here. 16 grams. That is 0.108 moles of oxygen. Okay.
We're trying to do it the other way to see if you could do it by going like the amount of oxygens in a water and the amount of oxygens in a carbon dioxide.
It's too hard. This one's easier. So then you're going to take your moles and compare. So I'm writing this out. So CHO, the lowest mole came from oxygen. So we're going to divide all the moles by oxygen. So that's going to be 0.2175 moles of carbon divided by 0.108 moles of oxygen. And this is 0.6515 moles of hydrogen divided by 0.108 moles of oxygen. And then this is oxygen divided by oxygen, so that's 0.108 moles of oxygen divided by 0.108 moles of oxygen. And these are 2, 6, and 1 when you divide them, and this is your empirical formula subscript. So the formula should be C2H6. Ta-da!
If you